Okay, so today I'm going to be going over the Test 3 exam. This covers Chapter 7, 8, and a little bit of Chapter 9. Okay, so the first question, what is the major product for the following reaction? So when I look at this, I think it's not an acid-base reaction because there's no easily available protons. So then, I always go through, is it acid-base? Is it substitution or elimination? Or is it something from Chapter 8 or beyond that we learned? So in this case, it's not acid-base, so substitution elimination, where there is a good leaving group and there is a strong nucleophile. So I'm going to go ahead and assume it's substitution or elimination. It's tert butoxide, so that's a bulky, strong nucleophile. So because it's bulky, or because it's strong, I'm going to assume it's going to be a 2, and because it's bulky, it's going to favor E2 over SN2. Also, once you know that it's E2, you have to ask yourself, is there a hydrogen that's antiperi planar? And because there's 3 hydrogens here and this could rotate, it can make an antiperi planar somewhere. And then the other question is it going to be saytseff or Hoffman? Well, if it's small, narrow, it'll make saytseff, which is more substituted. But in this case, it's big and bulky, so it'll be Hoffman product. So it should take a proton from right here. So all 3 of those are going to be hydrogens, which means you don't have to figure out which hydrogen's antiperi planar. They'll all be antiperi planar, and there's not an E or Z product formed. So this bulky nucleophile is going to come and take a proton from right there, and then the electrons from that proton will form a double bond between carbon 1 and carbon 2, and then the leaving group will leave, making your elimination product look like this. And notice the stereochemistry here is retained. This is a double bond, it just looks weird. The stereochemistry here is retained because nothing happened on this carbon to change anything. So that still will be a wedge. Sometimes I see this question, a really similar question, where they flip around the alkene and this becomes a dash, like the alkene's on this side. I don't know why people do that, but in this case, the stereochemistry is the same. The alkene's still on the correct side, so the right answer should be E. Okay, next question. Which reagents would you use given the reaction to gain the desired product? Okay, so if I'm looking at what happened here, I'm going to look at the transformation. We had an alkene, and now we don't have an alkene anymore, and we have an alcohol. And it looks like this methyl group has changed around. So first, we know we're adding 1 alcohol to an alkene and 1 hydrogen. So that's adding water. We know 3 ways to add alcohol or to add water. One is oxymercuration, demercuration. One is hydroboration. And one is acid catalyzed. So if I'm looking at all of these, then I know that hydroboration adds anti-Markovnikov, which would mean the alcohol goes to the less substituted side, so it can't be hydroboration. Oxymercuration does Markovnikov with no rearrangement, so the alcohol would go right here. So it's not that either because the alcohol is not there. So the only possibility is acid catalyzed because there does appear to be some rearrangement. So just to make sure, I'm actually going to draw this out, the mechanism. And so it'll add H+, and that would look like this with the hydrogen right here. And then there would be a methyl shift because this is a quaternary carbon. This is a secondary carbocation. It would be more stable if it traded places with that methyl group. There's still a hydrogen there, but it's implied, so I'm not going to draw it anymore. And then your water would come in and attack right at that carbocation. And you'd get OH, 2 plus. Water, and then that would undergo the deprotonation step. I usually just draw -H+, but you can also draw water, base, or something taking it out, and then this would be your final product. So that answer is right. Acid catalyzed hydration is right. But if you're not sure on this kind of question and you just know it's adding alcohol of some kind, you can eliminate KMNO4 cold because that adds 2 alcohols, and you can eliminate O3 because that cleaves the double bond, and then you've narrowed it down to 3 possible answers. And if you just at least remember that one has the possibility for rearrangement, then you can go for D, or you can narrow it down knowing that this is not anti-Markovnikov, just whatever you can do to eliminate wrong answers. Okay, the next question. So this is naming name the following compound. So my 3 steps for naming is number the parent chain, find all the functional groups, and combine everything. I think that you can likely solve this one with only doing a few of these steps. Like if you're not sure what that group would be called, that's fine. So it looks like the longest chain is 6, so that would be hexane. All these have hexane, so you can't eliminate any based on that. I'm going to start from this side because this methoxy group has high priority, and so does an alkene. So I know that the alkene starts at 3, so I can get rid of any, let's say we have 3-ene and 3-methoxy. I can get rid of anything that doesn't have 3-ene. So this is 4-ene, so that's not right. And then also, I know that the other substituent is at 3, so all these have 3 as well. So really, that didn't help me a ton. The next thing is I know that this has 3 substitutions, 1, 2, 3. So we're not going to be able to use cis-trans nomenclature. Cis-trans nomenclature is only useful if you have 2 substitutions on an alkene. If you have R1, R2, R3, you need to use EZ method. So I can eliminate A based on that, and I can also eliminate C based on that because it doesn't say cis or trans or E and Z. So now based on just knowing those things, just knowing how to number the parent chain and that I need EZ nomenclature, I've narrowed it down to D and E. So let's go ahead and find out if this is E or Z. So look at one carbon, so the first carbon on the alkene, and compare the priorities. And this is using the Kahn-Ingold pre-log system that we learned for R and S nomenclature. So you just look at the first point of attachment. This is a carbon and this is an oxygen. Oxygen has a higher molecular weight, so this is a higher priority. On this carbon, we have a carbon and a hydrogen. Carbon has a higher molecular weight than hydrogen, so this is a higher priority. So these are on the same side. E is antigen opposite. Z is zame. I would say Z, zame. They're on the same side, but Z and same kind of sound the same. So I'm going to say these are on the same side. Highest priority are both on the same side of this double bond. So then the right answer should be E. Okay. And then next question, what is the major product or products formed when trans 1,2-dibromo? So my first thing is I'm going to draw trans 1,2-bromo. So 1-bromo, 2-methyl, and they're trans. Goes dehydrohalogenation upon treatment with sodium ethoxide and ethanol. Okay, dehydrohalogenation is an E2 reaction. If you didn't know that based only on the name, sodium ethoxide is a nucleophile and it's a strong nucleophile, so we know it's E2. So when we have an E2, we need to ask, is there an antiperi planar hydrogen? And we need to ask, is it saytseff or Hoffman? Well, in this case, to tell if there's an antiperiplanar hydrogen, we actually have to go coaxial. So I always draw my bromine in the axial position pointing up. So if this is axial, this one would be equatorial. So this is also your dash there would be axial. So our bromine points straight up and our methyl group points straight down. If this could do an elimination between these two, there needed to be actually a hydrogen that was a dash. The hydrogen's not a dash. The hydrogen is a wedge, which means the hydrogen is right here. So these two aren't antiperiplanar together. But on the other side, there's actually hydrogens in both positions, both axial and equatorial. So this is a hydrogen available. So the only hydrogen available would actually be this dash right here. So that's the one that it's going to take. So it doesn't matter if it's saytseff or Hoffman because there's only one hydrogen that is available that's antiperiplanar. So the nucleophile is going to take that hydrogen. These electrons are going to leave this bond. The electrons are left behind, so they'll form a double bond, and the leaving group will leave all at once. And your final answer will be this. And it looks like that is answer choice B. C is one hydrogen away, so the leaving group was right here, so you can't form an alkene that far away. And then this was where there's not an antiperiplanar, so that's why that one doesn't work. And this one also, there's not a leaving group right off of the methyl. There'd have to be a leaving group there for that to work, and there wasn't one. So answer choice B. Okay, Markovnikov addition of HI to 2-methylbutene. So one thing I talk about with my students is when you have an addition to alkene, the first step is almost always that the alkene attacks because the alkene has excess electron density and it's going to find an electrophile. So that's going to be always the first step. So initial attack by iodide ion doesn't occur. Initial attack by iodine ion doesn't occur. Or iodine atom. It has to be the alkene attacks first. So we can get rid of A and B just knowing that. And then we usually don't see isomerization within an addition reaction, so that's probably not right. So then the only other options are carbocation at C2 or C3. I just realized I didn't draw methyl. 2-methyl-2-butene. So it would be right there. So the carbocation would in fact form at the carbon 2 where there's a methyl group because it would be more stable. So we had this HI attacks, and you would get your carbocation forming at the more substituted because tertiary is more stable than secondary for a carbocation, and hydrogen would add here. So the formation of carbocation at C2. So if you don't know anything else except that the alkene attacks first, you can narrow it down to get a 50-50 shot at a right answer. And beyond that, if you know that the carbocation is going to form at the more stable and there's a methyl right there, then D would be your right answer. So you don't even have to know the whole reaction. You just need to know those few steps. Okay, what is the major product of the following reaction? Again, this does not look like an acid-base reaction to me because there's not an acidic proton available. So then I'm going to ask substitution or elimination. There's a good leaving group and a strong nucleophile, so I'm going to say that's substitution or elimination. It's a strong nucleophile, ETO-, so that's going to be 2, and there's heat, which makes me think it favors E2. Then you have to ask yourself, is this saytseff or Hoffman? Well, this is pretty narrow, so I'm going to say it's saytseff. And you also have to make sure there's an antiperiplanar hydrogen. So let's look at our leaving group right here. There's only 2 places you could take a hydrogen from, here or here. But here, actually, there's 1, 2, 3, 4 carbons. So there's not a hydrogen available there. So the only place that there's a hydrogen at all, much less an antiperiplanar one, is at this carbon right here. And all 3 of them are hydrogen. So all of them would be available. So that means the elimination reaction is going to take place there. It doesn't really matter if it's saytseff or Hoffman because there's not hydrogen available. So that ETO-, ethoxide is going to take a hydrogen. The electrons are going to form the double bond between electrons that get left behind when this proton is stolen will form a double bond right here, and then the leaving group will leave. And the rest of the atom doesn't change. There's still a methyl group right here. This bromine has left and a double bond is formed right here, and that should be your right answer. That's answer choice C. Okay, next, HBr. So this is very similar to the last reaction that we looked at on HI addition. So the first step is always going to be, or I guess I should say, I go through this and say this doesn't look like an acid base because although there is an acidic proton, there's not a great base present. So then I ask, is it substitution or elimination? Well, there's not a good leaving group, so it's not substitution or elimination. And then that leaves us with chapter 8 that we learned from this chapter. So it's going to be some kind of an addition to this alkene, and that checks out because there's an alkene right here and HBr. And we know with additions to alkene, the first step is always that alkene is going to find something positive that can attack, like there's a partial positive on this hydrogen and a partial negative here because there's extra electrons in that double bond, right? That pi bond has high electron density. So on that first step, you'll get the addition of a hydrogen and the carbocation over here. The hydrogen adds outside because the carbocation will go to the secondary carbon that way, and it's more stable. But whenever you see a carbocation, you have to ask yourself, is there going to be elimination? Or I'm sorry, is there going to be rearrangement? And in this case, there would be rearrangement. If the carbocation moves one over, did I get the right number? 1, 2. Yes, if the carbocation moves one carbon over to right here, it's going to be more stable than at the secondary position. That hydrogen's still there, but it's implied hydrogen, so I'm not going to draw it out. And then you also got Br minus in this first step. So that Br minus is going to come in and attack right there at the implied hydrogen, and you'll have a bromine and a methyl group right there. This actually, because it's a carbocation, it's sp2 hybridized, which means it's a flat plane, and the nucleophile can attack from the top or the bottom, so it will give a racemic mixture. Okay, so the only one that has the bromine and the methyl group on the same is answer choice C, so it's got to be right. Okay, what mechanistic step in the acid-catalyzed dehydration of 3,3-dimethyl 2-butanol is the rate-determining step? Okay, well, this is 1, 2, 3, 4. This is 3,3-dimethyl butanol, and it's undergoing acid-catalyzed dehydration. So the first step of acid-catalyzed dehydration is always that this alcohol gets protonated, so that's step 1. And then the leaving group leaves, forming a carbocation. That is always going to be the highest energy step in a reaction that forms a carbocation because carbocations aren't very stable. And we talked about that a lot when we talked about E1 and SN1 reactions. And this is just a special type of E1 reaction, so that hasn't changed. So that should be the right answer. And that hopefully was a pretty easy one for you guys to get because you have done this, this material for a while. Okay, what is the major product of the reaction of the following what is the major product of the following reaction sequence? I just realized that was in here twice. Of the following reaction sequence. So, okay, there's not a clear nucleophile. This is not an acid base because there's not a clear proton that would be given up. This is not a substitution or elimination because there's not a good leaving group and a good nucleophile. So the only other thing would be some kind of an addition. Whenever you see hydrogen and some kind of metal, as long as it's not a poison catalyst, it's going to take any double or triple bond and take it all the way down to the alkane. So that first step is going to be making the alkene into an alkane. And it won't change the stereochemistry of anything else at that step because it's only performing on this hydrogen. They do add syn, but there's 2 other hydrogens there, so there's no stereocenter. And then the next is ethanol and heat. So again, I'm going to go down my list. This doesn't look like acid-base because there's no easily available protons. So then it must be substitution or elimination because there's a good leaving group. Ethanol is a weak nucleophile, but it is a nucleophile, and with heat, that will do an E1 reaction. So this leaving group will leave, and you'll get a carbocation. But this carbocation is directly adjacent to a quaternary carbon. Anytime you see a carbocation, you always have to ask yourself, is there going to be a rearrangement? And in this case, of course, there will be rearrangement. The methyl group will shift over, you'll get a methyl shift, and you'll have the carbocation move over. Okay? And then because you have heat, it's an elimination reaction. The hydrogen can either be taken from here or here. But to make the more stable option, you're going to take the more substituted. This is a narrow nucleophile. It's going to take the more substituted option. So the ethanol is going to come in, take that hydrogen. The protons are going to fill in here, and you'll end up with, let's see, 1, 2, this structure. So let's see which one of these looks right. This one didn't undergo rearrangement. This one looks like it didn't undergo rearrangement either. This one did a substitution reaction. That would be a side product, but it would not be the major product. And so the right answer should be answer choice A. Okay, the next question is a multi-step reaction. I love multi-step synthesis questions. Oh wait, this isn't a multi-step synthesis. It's which of the following would yield 2-pentyne. So you just have to be able to know all of these cold turkey. Well, the first one is actually, this is a multi-step synthesis. If you have alkyne with NaNH2, is that an acid-base reaction? Actually, the answer is yes, because this proton is readily available. It's 25. So, and this is a good base. So it'll take this and leave this behind. So the answer to the first part is you make an carbanion, which is a good nucleophile. And if you mix that in with this right here, it'll come in and attack and kick that out. And you'll have, let's see, 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I always count my carbons. You'll see this did an SN2 reaction. This attacked the primary leaving group left. And so this is 1, 2, 3 carbons, and the one that attacked is 4, 5. A carbon bond took place between this carbon on the alkyne and carbon 3 or carbon 1, however you want to think about it, on the substrate. But this is not 2-pentyne, this is 1-pentyne. So it does make pentyne, but not the right one. Similarly, you have the same reaction initially on this first step, only a different acid to give up its proton. But this acid-base reaction gives up its proton, turns this to a carbanion. And then you have this bromine, and so it'll attack and kick out. And so you still have this part, but it forms a bond right here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is pentyne, and it's 2-pentyne, so I think that's probably the right answer. I'm going to go through the rest of them. This is a weak nucleophile, so I think this would maybe do an E1 reaction, but at best it would do, I don't think it would really do much. There's no heat, so I think it would do an SN1 reaction actually, because it's not an acid-base reaction. There's not really good proton available. And for substitution and elimination, it does have 2 good leaving groups, so it could undergo 2 eliminations under the right conditions. But this is a weak nucleophile, so it would be on the one side. It could theoretically do E1, but there's not heat, so it would favor SN1. So I don't really think this is going to be the best way to yield 2-pentyne, if at all. And we did learn when you want to do this double elimination, NaNH2 is actually one of the best nucleophiles you can use. If you did HA in heat, hopefully you recognize that's an E1 reaction, and it gives you an alkene, but there's only one leaving group, so it doesn't give you an alkyne. And then for this last one, let's see, it's not an acid-base reaction. This is a good nucleophile. This is ethoxide. So this is probably going to be a substitution or elimination reaction, but this is not bulky and there's no heat, so I think this would actually favor SN2. So B is going to be your best answer. Okay, 11. What is the major product of the following reaction sequence? This is another multi-step synthesis. And we start with HI. So there's not a clear acid-base reaction because there's not a good base. This would be a good acid, though. So instead, we have to go down our list. Is it substitution or elimination? No, there's not a good leaving group. So it must be an addition of an alkene to some kind. And the first step always, in addition to an alkene, is the alkene attacks. So the hydrogen would add right here and the carbocation here. Whenever you see a carbocation, you always have to stop and think, is there rearrangement? And in this case, there will be. This hydrogen will shift over because being a secondary is not as good as being a tertiary carbocation. So the tertiary shifts over here, and this right here, this hydrogen is still there, but I'm just not drawing it because it's implied. The next step would be this iodine that was generated in the first step, I minus, when this bond broke, is going to come in and attack. So you're going to end up with this structure, I, right there. Okay, and then the next step is tert butoxide. So tert butoxide, when I see tert butoxide, I'll immediately think E2 because It's not going to be an acid-base reaction. There's not an obvious proton to take out. So then it has to be substitution or elimination. It's butoxide. It's O-, so that's strong. So it's going to be SN2 or E2. But it's big and bulky, and this is on a tertiary carbon. So it's definitely going to be an E2 reaction, not an SN2 reaction. So once we know it's going to be an E2 reaction, the next thing to do is ask ourselves, is there an antiperiplanar hydrogen? Well, both of these hydrogens here can rotate and line up an antiperiplanar, no problem. And then over here, there are 3. So yeah, all of those would be options. So then we ask saytseff or Hoffman. Well, this is definitely big and bulky, so it's going to favor Hoffman product. This is the least substituted, so I'm going to say your tert butoxide will come and take the least substituted hydrogen or the hydrogen to make the least substituted alkene, and your leaving group will leave. So that leaves this structure. And when you first look, it's like, wait, I don't see this structure actually on here. That's definitely not D because that's an alkyne. This is if it formed right here, and we know that's not it. And then these two are both tempting, but actually B, if you just let this carbon rotate here, looks like the right answer. So don't get freaked out too much if you don't see the right answer right away. Try to think about how the carbon bonds might rotate. And as long as you have 1, 2, 3, 4, 5 on your carbon chain, 1, 2, 3, 4, 5, and right at carbon 3, you've got an alkene coming off, that's the right answer. I made that into an alkyne, but I was just drawing to emphasize it. Okay, so that's B. I think that one's kind of a trickier question. Next one, what's the major product of this reaction? So first step, this is not an obvious acid or base, so it must be substitution or elimination. It's got a strong nucleophile and heat, so strong nucleophile makes it 2, and heat makes it E2. With E2, you have to make sure that it's antiperiplanar. Well, both of these have hydrogens at both places, so it will be antiperiplanar, no problem with that. And these are actually symmetrical, so it doesn't matter which one we take. So O- will come in and take one of these. The electrons left behind will form the double bond, and the leaving group will leave. And you'll end up with this structure right here. Next is O3, and this is 2B, is just like part of the solvent system. So whenever I see O3, I'm like, okay, we're cleaving that alkene. So actually, I leave everything looking exactly the same. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. So there should be one more carbon here, 4, and that carbon has a double bond off of it. That's a hard drawing to see. But then once I've just drawn it right in there to make sure that I have everything, then I open up my chain. 1, 2, 3, 4. And off of 4 is where the double bond was, and that double bond had a hydrogen here. Okay, so you always should number to make sure that you're not losing a carbon. So there's 1, 2, 3, 4, 5 on this ring, and 1, 2, 3, 4, 5 on this ring. Oh, but this one's wrong because it has an aldehyde instead of a ketone. This one's wrong because how would you make that giant ring? We don't even know. To get this product, you'd get the alkene in the first step, but then add cold KMnO4 or osmium oxide. So if you just know that it cleaves and this one doesn't have a hydrogen there, it would be a ketone, then you can pick D. But just in case, let's make sure that we number it 4, 5, and then 1, 2, 3, 4, 5. So we didn't lose any of our hydrogens there, so that's the right answer. Sorry, that was confusing. I always try to make sure that I number my hydrogen so I don't lose one. So that's what happens. Okay, the major product of this is not an acid-base reaction because there's no obvious hydrogen that's available and no base. So then the next option is going to be substitution or elimination. Well, there's not a good leaving group and there's not a good nucleophile. So it's not that. So it must be from chapter 8. And in fact, this is an addition of an alkene. It actually adds 2 bromines and they add anti. So one's a wedge and one's a dash. So if you draw one as a wedge and one as a dash, But then you rotate it to where it's a Fisher projection. Your dash, as you rotate a dash, if this is pointing backwards towards you, and then you rotate it so it's a Fisher projection, it becomes a wedge. So actually, equal amounts of 1 and 2 are the right answer, because it does this plus the enantiomer. So this plus the enantiomer on the Fisher projection would be 1 and 2, because you're looking down from the top with them both like this. So CH3 is going directly away from you. And then if you're looking from the top, the bromine would be on your left and the hydrogen would be on the right. Bromine would be on the left, hydrogen would be on the right. And so there you go. This is a pretty complicated question, but we also talked about this in the review that we did in class on Wednesday. It was literally this exact same question. So that's why I think it's really important that you guys go back and review those quizzes, the quizzes online, Q, I, Z, Z, I, Z, that we do as review, because they're really helpful. Okay, which reaction is regioselective? Okay, regioselective means two different things add differently. So Markovnikov or anti-Markovnikov. So we know BH3-THF is regioselective because it adds anti-Markovnikov. And osmium oxide actually adds syn, but the same thing is added both sides. That's syn is stereochemistry. Same thing is added to both sides. So it's not regioselective, it's stereoselective. Br2, same thing is added to both sides. It is stereoselective. It adds anti, but that's stereoselective, not regioselective. There's not anti-Markov or Markovnikov. If you had Br2 with water as a solvent, it would be OH, but we don't have that here. And then HCl actually does add stereoselectively because the alkene would attack, and you'd get the carbocation with the H here, and then the Cl minus would come in and attack. So this actually adds Markovnikov. So 1 and 4 are both regioselective. Okay, how many peaks would you expect in this spectrum? So I'm going to draw it. CH2, CH2O, CH3. Oh wait, I think I lost 1, 2, 3, 4 carbons. Yeah, 1, 2, 3, and 4 carbons. Okay. So I actually see a plane of symmetry here right through the middle. So this CH2 and this CH2 are in exactly the same environment, and this CH3 and this CH3 are in the same environment. So I think there would be two unique signals. And the question doesn't ask this, but the signals on this one is 3, and this one is 2, but it's mirror image. So they would be a 2 to 3 ratio or a 4 to 6 ratio. And you'd have to compare if it's 2 to 3 ratio to here, and you would need to realize there's 2, 3, but that's not my total number of hydrogens. My total number of hydrogens is 10. So it must be that there's 4 to 6. And the splitting on this, actually there'd be no splitting here or here because of the plane of symmetry. So the right answer here would be 2. Okay, I don't think there would be splitting on the plane of symmetry. That's more advanced in this class anyway. Okay, which structure is consistent with this 1H NMR spectrum? The peak at 1.7 is non-net. Okay, that's a huge hint. So, we get a bunch of different information from here. We see that there's 6, 7, 8, 9, 10 hydrogens. So we need to look for 10 hydrogens or a multiplet of that, like 20 hydrogens. And then one of those hydrogens is a non-net. So one hydrogen is a non-net, which means N plus 1 equals 9, which means N equals 8. So there's 8 neighbors at one of those hydrogens. So if I just know those two things, I'm going to look to make sure these all have 10 hydrogens and then that one of them has a bunch of neighbors. And I'm going to draw these out because that's easier. CH3COH, CH3, CH2, 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 CH3, CH2, CH2. 1, 2, 3, 4. 1, 2, 3, 4. Okay. CH3, CH3, CH, CH2OH, CH3, CH2, CH2, CH3, OH. Okay. So let's see. All of these have an alcohol. I'm assuming that is probably this peak here. So that's the same for all of them. Do any of these hydrogens have 8 neighbors? There's not a hydrogen here, so this doesn't. And all 3 of these are in the same unique environment, so no, these would appear as a singlet. So no, you would need, for this one, you'd need a singlet where H is equivalent to 3, 6, 9. We don't have that in this feature, so we know A is wrong. This hydrogen, these hydrogens have 1, 2, 3, 4, 5 neighbors. Same with this one, 1, 2, 3, 4. So none of these hydrogens have 9 neighbors. Let's see, 1, 2, 3, 4. Yeah, so this one can't be it. This hydrogen has 3, 6, 7, 8. So I'm going to go ahead and say this is probably my right answer, but I just want to make sure. 1, 2, 3. This hydrogen has 1, 2, 3 neighbors on this side, but only 2 on this side, so this doesn't have 8 either. I'm going to make sure the other features of this match up. So if I'm looking at this, I predict this hydrogen has 1, 2, 3, 4, 5, 6, 7, 8 neighbors. So one hydrogen with a split of 9 for n plus 1. And then these 3 hydrogens, these 1, 2, 3, 4, 5, 6, 6 hydrogens, they're in the same unique environment, split into a doublet because their neighbor is this one hydrogen. And then 2 hydrogens that have 1 neighbor, so also split into a doublet because n plus 1, they have 1 neighbor, so 1 plus 1 is 2. And then 1 hydrogen, that's a singlet from the alcohol. So let's see, we have 1 hydrogen split into 9, 6 hydrogens split into a doublet, 2 hydrogens split into a doublet, and 1 hydrogen split into a singlet. And that's how I figured out that this unique peak belonged to this carbon, this structure C, and then also how structure C fits the rest of these peaks. This was a bonus question, so it's a little complicated, but hopefully that was helpful for you. Okay, well, that's the